playlist, which is really helpful, because if they're all like just, I don't know, yeah, I'm not.
They're in the same
sure.
playlist.
Really?
Yeah, it's called, I'll send you the link again.
Okay.
So I have it by date, and then someone suggested I write the order of the video by the date too. So I've been doing that.
Okay. All right.
If you send me an email to nudge me and remind me, I'll send out that link again to the playlist. So I had some comments as people were working on the homework that maybe if you haven't had a chance to do proofs in the past and you feel uncomfortable with it, remember that you have to tell yourself that writing proofs takes time. And it's we were just talking about this today in our department because one of the suggestions were that we have cumulative finals to wrap the material together. And I kind of felt like something like abstract algebra is not like that. It's not a body of material like Calc 2 that you're trying to pull together. It's a process and an art, and as you learn it, you'll get more comfortable with it. Abstract algebra classes always tell me that the material seems easier towards the end of the class than it did at the beginning. That means they're mastering the idea of putting together the proofs. So that's the good thing, that it's part of learning, that you just learn how to do this as a process as time wears on. And you can go and look on Rate My Professors. You'll see every group of students that were in pure math classes, at the end of them they say, I know how to write a proof. So if all of them could do it, they're just like you, that you can do it too. And if I can do it, you can do it too. Because there's nothing special about me. I promise you about that. It's a thing that's learned. And I told you that as I was learning it, I was thinking to myself, if I only had the chance to teach this one day, I would put what's in my mind out there, the process. That was what was missing in my other proofwriting classes. The process wasn't taught. It's almost like they had these finished, polished proofs, and I had no idea where they're coming. They were beautiful. I had no idea where they're coming from. So that's how I'm going to present the solutions to you, and the more you see, the more you'll get used to. For those of you who feel like you've already mastered the art of proof and want more, come on, I'll give you more. So it's great. You can do it in lieu of some of the stuff we're doing in class. I can give you some other things to think about. I have no problem with that either. So what do they call that? Differentiated instruction? All right, so this is number 29. And some of the process in 29 and my thinking, I didn't put in this solution. And I'll post these solutions. Obviously, I couldn't post them before the quiz. I didn't put in there because I kind of thought it was messy. But the problem here told you that you have a finite group, you have an identity, an even number of elements, and then they want you to prove that there's an element that's not the identity such that A star A is equal to E. So my know is that stuff between the if and the then. I know it's a finite group, and I know it has an even number of elements. So I always try to write things symbolically. If you've had me before, you'll hear me say that you can't really work with something unless you have some kind of formula to move around. So every chance I get, I try to expand that into some kind of numerical or formula. So I just put that the number of elements in G, which is the absolute value symbol, is equal to 2n, where n is a positive integer. So I always try to think in that way, some way formulaically. Because if you can't, you're just staring at a bunch of words. The show is that there is an A not equal to E, such that A star A is equal to E. So that's the part after the then. So if you look at that, I just felt like there was nothing to get my hands on. So there was a bunch of, what I meant was there's no formulas that I'm putting together and getting to, aha, at the end, here's my A. So there was nothing I felt I could start with. So I was indeed looking at a bunch of words. So the first thing I did is I said, okay, what's so special about even number of elements? So I looked at the no that they gave me. 1, finite group. 2, even number of elements. That even number of elements seems very specific. Why doesn't it work for an odd number of elements? Why is that so important? So the very first thing I did is what I call experimentation, numerical experimentation. I just started out with 3 elements, and I tried to make up a group that didn't have an A squared equal to, and I was able to do that. I was able to create such an animal. Then I went to 4. When I went to 4, what I tried to do is I tried to force it so that it wouldn't have an element with A star A is equal to E. So I made the Cayley table and I tried to lay out the elements, and I kept getting cornered. So I would, I don't know, you should actually do this yourself, and I should have actually put the work here, but I was, I was pretty messy. And next time I'll put that kind of experimentation there. I wanted to see what was so special about 4 versus 3. And you can do that little experiment. How many of you tried that? Just said, what's the deal with 4? You find yourself cornered every time, like every time you try to force the statement to not be true, and try to understand why it's working out. So what I realized is eventually I had to use the same process I was using with the 4 elements, trying to not get it to be true, and then come up with some problem. So as I was playing with this 4-element group and trying to create this animal where A star A was not equal to E ever, I kept getting cornered, and I started realizing that there was a reason why I was getting cornered. And I was trying to figure out if there was a way to generalize why I was getting cornered, that reason. And the way I thought I could do that was by contradiction. So assume there doesn't exist any element, just like I was playing with the 4-element set, that doesn't end up with A star A equals E. Well, that means that A is not equal to its own inverse for any A. That's what you'll realize if you're playing with the 4-element set, that you can't have any element be its own inverse as you're playing around. And you can also see that by the cancellation property. I can just put A inverse on both sides and get that to happen. And so that's true by cancellation law and property of inverse. So then I listed out the elements. So now I'm going through the process that I did with the 4-element set and trying to corner myself in the same way, but I'm doing it with an arbitrary number. So what I noticed is as I was building that table with 4 elements, and I never went to 6, I just messed with 4. What I noticed is, well, I had E, and with E you get the Cayley table to fill out and everything's defined. It's the other stuff, everything after E, that's kind of interesting. So I labeled everything after E. Well, if I pulled out E as its own element, how many elements what kind of elements am I going to have left? I'm going to have an odd number of elements left, right? So I'm going to subscript all those elements, number 1, number 2, all the way up to 2n minus 1. So that's my null. When students first are writing proofs with me, I tell them that every piece of the no, when you see it being used, wave a little flag. I'm using my no. So here it is. I'm using my no. That's when you know you filled in enough detail. If you didn't fill that in anywhere, then you're not putting enough detail in. So what I did for the trying to get it to go wrong with the 4 elements is I said I could just reorder things, right? For example, that x1 through x2n minus 1, it can't be its own inverse. x1 inverse can't be itself again. So I'm just going to take one of those elements left in the set and make it be the other inverse, the inverse of x1. And I can subscript them any way I want. So I'm just going to let x2 be the inverse of x1. But then x1 must be the inverse of x2, vice versa. They're paired. They're gone. Well, what's left? Kind of like I did with the 4-element. You'll only understand what I'm talking about if you did this little experiment with the 4. You're an experimentalist, right? So you can experiment and just see what happens. If I took those 2 are taken care of, then I have x3, x4, that's what's left. Well, then I can do the same thing with the next 2 elements. I'll take x3 and pair them with x4. Just like I did above. So those 2 guys are gone, taken care of. What's going to happen?
The last one has to be paired with E or be its own inverse.
Right, I'm dead, right? I'm cornered. So I've now symbolically explained what happens with my cornering. So the problem occurs when I get to the last one, x2n minus 1. There's nothing left in the set anymore for something to be its inverse, other than E, which E is not, by my contradiction assumption, it's not its inverse. So it has no inverse to pair with, so it's in a violation of G being a group, right? Everything's got its inverse. So this is the proof that I would have seen in a class where there was no instruction of how to write a proof. So assume G has 2n elements by hypothesis. Let us assume, on the contrary, without any discussion of why I'm doing that that there does not exist an element such that a squared is e, not a, e. This is equivalent to A inverse not being equal to A for any A and G. I may list the non-identity elements of G. You know, this is math language, right? My son says this is how math teachers talk. I may list the non-identity elements of G as x1, x2, da 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 da. So I mentioned that here, my little arrow after the fact, that's by property of inverse and cancellation law for a group. And note that there's an odd number. Math talk, right? Note, there's an odd number. To each element in this set, we can reorder the indices so the inverse of xi is not xi. Like so. It's a textbook proof now. This is so clean. But then as we are pairing, x2n minus 1 has no remaining elements to pair to. Therefore, our assumption is false, and there does exist some a not equal to e with a squared is equal to e.